done some literature research, and I'm very well prepared to report on approach number 1, how to regularize the moduli space following Bernd-Siebert, and the buzzword, at least as he phrases it in his papers, of Euler class on Banach orbifolds. Now, I want to make our life easier and not have to talk about orbifolds, so I would like to think about his approach just sort of in the context of manifolds, which has something to do with having trivial isotropy. But just so that I'm not completely cheating, I'm going to give you a little bit of an executive summary of what one does with isotropy and what that was again. So, basic reminder here. So, for a holomorphic map, we called it stable if isotropy or stabilizer are finite, and stabilizer is in this case, right, our group action here is the reparameterizations, and we're looking for it. So the stabilizers are the fixed points of the group action. Stabilizer makes more sense in this, when you think about the group action, but I guess they're also called the isotropy groups, and eventually there's not going to be group actions, but sort of more general morphisms in categories, and then isotropy is somehow a better word for that. So, right. Example where that happens is, let's see, I want to look at multiple covers of simple spheres. So I'm going to factor, this P1 is my surface, and then there's another P1, that's my symplectic manifold. There's a silly holomorphic map, that's simply the identity. And then there's a multiple cover. K-fold cover. Right. So those are holomorphic functions, so all of these are holomorphic curves. Right? And the question is, so what is the stabilizer of UK? Right. So here we also, we have to decide what group we actually wanted to quotient out by, and I think, right, we usually put one mark point at infinity that we'd like to fix. So within that four-dimensional automorphism group, let's look at the stabilizers. So those are all Möbius transformations of particular easy form. Right. And so if you ask yourself, what is UK composed with one of these phi's? Well, that is maps Z to right, so first we reparameterize AZ plus B. Then we apply our map UK, which goes to C to the K. Whereas UK maps C to Z to the K. Right, and well, the two are equal pretty much exactly if a to the k is 1 and b is 0. Big surprise, right? We have stabilizer group being the kth root of unity. So that's where isotropy comes from, right? And we call this nontrivial isotropy because there's a nontrivial stabilizer group. So again, mantra from earlier is, these things come sort of with two meanings for our examples. One example was that these were holomorphic curves that were nowhere injective. They also happen to have non-trivial stabilizers, but those are two different examples. That doesn't always come together. So, this here. So the question is, what do you do about this? In this very simple example, that was probably a perfectly fine regular holomorphic curve, and so you could have just used that J here to cut out your space of holomorphic maps and then quotient by the automorphism group. So if that's a fine smooth manifold and the automorphism group still acts on it, what happens here is that it acts with finite stabilizer. And so what you can do is you can take sort of a local slice to the group action here, where you're sort of quotienting the continuous part of you're quotienting sort of just by the tangent space of the automorphism group, and this finitely many elements sort of still act on that local slice. So that gives us something called an orbifold structure. So locally this looks like the perpendicular complement to a group orbit, modulo modulo something. So on this, the stabilizer. Oh, I see. What I meant to say here is it locally looks like sort of this complement in the zero set. We're thinking of linearizing that modulo the stabilizer at that point. Right? So if you've seen orbifolds, great, that's the local model for it. If you haven't seen them, you're very briefly seeing them today.
Is that also just for discrete?
That's just for discrete, yes.
Yeah.
Orbifold means it's a finite group. Yeah. Yes.
So you're saying that nowhere injectivity and non-trivial isotropy don't always come together, but isn't it true that if you have somewhere injectivity, then you have trivial isotropy?
Yes, simply because if you check this out, then
Means that either
if it's everywhere injective, then clearly your isotropy has to be trivial.
I mean,
right?
even if it's somewhere injective.
If it's somewhere injective, if you have an open set, right, and then you need to know that your automorphisms, if they're the identity on an open set, they're the identity everywhere. So, yeah, in one direction that goes.
Okay.
Yes. Right. So, that's not so bad a story when you have an equivariant transverse perturbation to start off with. So that's the geometric regularization story. Oops. The abstract story, unfortunately, is a little bit more complicated, which is why I'm only going to give you a buzzword for it. So, right, we generally don't have equivariant transversality. In fact, even when you have a finite group acting, which we'll look at some examples. And so in the abstract world, you end up working with multi-valued perturbations, which then give somehow well-defined counts, but in the rational numbers. We'll see a little bit how that works. I'm not actually going to really define what a multi-valued perturbation is, but try to give you an impression. So, so silliest example is the trivial bundle over S1 with fiber R, and a Z2 action that actually, fixes the base point on S1 and just flips in R. So the generator acts on C, X by just multiplying the X with -1. Well, if I now wanted any equivariant section of this, the defining equation for equivariance reads that f of z is equal to minus f of z. That's not so good, So the only equivariant section is f equal to 0, which most definitely has 0 differential, which is very much not transverse. So what can we do? Well, there certainly is a transverse section of this, right? So for example, just mapping every z to some epsilon constant. That's not 0. That's certainly transverse, because it has no zeros, and which it even would need to have non-zero derivative. But it's not equivariant. But from this we could make a multi-valued section, which I guess I'd call f underline. So, and just as the name somehow betrays, at a point z, it's just allowed to have several values. For example, in this case, I can take this section and I can move it around by my action. So I'm going to take s of c and minus s of c. Each one of these is transverse, so you'd call this also to be transverse. And now it is Z2 equivariant because, as a set, this is equivariant. This is invariant under multiplication with -1. So then the only question is, how do I count zeros? But in this case, there's not really a question because there are simply no zeros. Right? That is most definitely the empty set, and so before we even try to decide how to count, clearly we should get 0 out. And now you could go in and try to do other things. Instead of this constant s, I could have tried, something that has like 2 transverse zeros, like a sine function. I double it up, I would get somehow each one of these would have 2 transverse zeros. But again, each one of them also, the signs of the 2 zeros already add to 0, so it's not much of a. This is not a place where we're going to see rational numbers come. We're not going to need rational numbers here to make sense of that count. right. So, yeah. So we need something a little bit more fancy and interesting to think about where rational numbers might come from. Also, right, the other thing with this example is that there's not actually even an action on the base. So it's not, the sort of quotienting by Z2 here, that I really ought to be doing, because I'm looking at zero sets modulo the action. Makes no difference here. So I was trying to find an example where I actually have some action on the base. And I can't get transversality. Maybe for a slightly more refined reason. So here's the easiest one that I came up with. I'll give cookies are rewarded for examples between 0 and 1. So here I'm taking, again, a trivial bundle over S2, so I'm sort of expecting the count to be 0 at the end of the day, sadly. But let's see. So C4 is my fourth roots of unity. I should say how they act on a point. And so here I'm going to think of S2 as C union infinity. And I'm going to act on the base simply with Z4. But in the fiber, I'm going to act sort of only with Z2 by squaring things before I multiply. So let's see. I now have a equivariant section. I'd better have, let's see, if I multiply by -1 in the base, that squares to 1, so I'd better get, goodness, what just happened? F of minus x is, oh, hold on, right. F of ix now needs to be minus f of x. In particular, if I throw in x equal to 0, right, what I should say is, okay, so this action, the Z4 action here has two fixed points, one at 0, one at infinity. Right? And so those are the places where we expect, obstructions to equivariant transversality. So, and this is 0 works exactly the same way at infinity. So, if I take this at x equal to 0, that tells me that f of 0 better be 0. Can I make a transverse though? Let's see about derivatives. Right, so if I have any path that goes through 0, what does this action tell me about values to the left and the right of 0? So that's where I want to look at f of minus x. And unfortunately, here my equivariance tells me that I better have the same value before and after, which means I can only hit 0, well, if I'm constant 0, or it's going to be some kind of tangency. So, and that works in every direction, so the differential is supposed to be 0. Alas. So, not transverse to 0. But there's only 2 points now, right? So, now again, I could, go multi-valued, but I can do the same silly trick again. I could take f of x to be plus epsilon and minus epsilon. Yeah. Then, no matter which gamma I plug in here, this is always going to be symmetric under multiplication with -1 or whatever. So I have no zeros, so still my zero set, even if I mod out by the Z4, is the empty set. So my count is still 0. Sadly. Right. So finally, one example where we're expecting a non-zero count. However, this is an example where I'm not entirely sure that you can't find an equivariant transverse perturbation. So, I haven't thought about that too much. But let's see. So, I'm going to take the tangent bundle to my sphere, and I'm going to act on S2 by rotation with, Z3, or group of order 3. And that induces a rotation on the tangent fibers. All right, so in the same, identification as third roots of unity, gamma now acts on a base point x in S2 and a vector at Tx S2 simply by multiplying x, or rotating, and pushing forward the tangent vector with that same action, whatever that might be. So let's see how I should. So here's my S2. And I have rotations by 1/3 and 2/3. So but again, there's 2 fixed points. So I'm not going to check whether or not I have an equivariant section. I'm just going to take a section. So let me take a transverse section. And we all know and believe that that will have to have at least 2 zeros, and that we can find certainly some that have 2 zeros. I'd just like them to not be at the fixed points. So let me put them somewhere nice. For example, here and there. But that already looks like it's not Z3 equivariant, right? If that was Z3 equivariant, I would have 3 more zeros from each one of them. And that's in fact what happens if I just take that transverse section and I make a multi-valued transverse one from it. Right, so I want this to be transverse also. And I do this by, let's see, f of x. So I'm just going to start with the silly one. Clearly I'd like my section here. Right. Then I would like so as a set, I would like f at gamma x to be equal to the push forward of the set f at x. Well, so this here is now contains certainly the point s of gamma x, and here my first choice gives me gamma star S of x. Those are probably not the same, so I'm just going to artificially add another section that makes up for that. So let me do the, right, so I'm going to have to push it forward. But I want to undo this gamma x. So here I'm going to take gamma in, oops, s. Inverse x. And then I do the same thing with that one. I take gamma square s of gamma minus 2x. Right, so let's see whether that checks out. Right, if I apply gamma here, I'm seeing gamma star s of x. That's good news, because that cancels these two. If I apply gamma in here, I'm losing one of the gammas, so that's gamma square star s of gamma inverse x. Let's see what I get here. So I'm supposed to just push forward with gamma, so I'm seeing gamma square push forward s of gamma inverse x. That's also good news, because that's exactly this guy. And the interesting thing, well, of course we're going to need the fact that the group is cyclic at some point. So that's going to happen here. If I push that forward once more, the gamma squared gets killed. So I'm just going to see s of gamma minus 2x, also known as s of gamma x, which is the first guy here.
So no matter what your group action is, can't you always use this trick to start with
right.
Any section
You can
and form
always
an
do that.
equivariant section?
Yes, pretty much. Yeah. I mean, so this works because I have a global quotient here.
Yeah.
Right? Yeah. If you take one section, you push it around, you get an equivariant transverse multisection. So that always works. Here in this formulation, it also makes a little bit more sense to sort of explain the meaning multisection. Here, of course, it's just f is given by 3 sections. Each of these is a section in its own right. In general, we will allow this point set on the right-hand side of f to come from sections that are only locally defined. But if we're talking about it being transverse or smooth, what we're asking is that this set on the right-hand side is locally represented by a number of smooth transverse sections. That's the deep mystery here. So, but now let's see how what are we getting in terms of zero set. And now I would actually really like to quotient out. So, well, a priori, let's see, right? So S has 2 zeros. I'm pushing them around, so I'm going to see, F. Multisection is going to have, well, try to apply rotations. So rotation by 1/3, and then is a rotation to the back. So 3 points, right, for each one of these. But I ought to really look at the zero set mod Z3. Let me look at this on the actual global quotient. So this, the way we like to draw these orbifolds is to really indicate that there's sort of a, singularity that you got by quotienting by Z3 at that fixed point. So this equator down here gets 3 times covered. So fixed points become singularities, and the zero set now is 1. Yeah, 0 for each of those two. So we ought to count them, and the rule here is that you count it with 1 over the number of zeros that get mapped there. So there are 3 here. There are 3 here. And so that means when you count this, and then we have to debate signs. Up here the sign, is +1 because the Euler characteristic is supposed to be 2. And so if the quotienting is at all orientable, both signs are going to be +1 also. So that's where we get a rational number, and I believe that is somehow known to be the Euler characteristic of this singular S2. That's where rational numbers come from, in this story at least. And these were all global quotients, our big moduli spaces here. You have sort of different isotropy groups at different holomorphic curves. So odds are you can only locally describe them as quotients. So that's why we're expecting term to go way out of this simple way of making multi-value perturbations. Right. So that was all the sort of warm-up examples to make you. And now here's the sort of large-scale philosophy of what one does. So when I say isotropy, we always mean non-trivial isotropy. So in the world of analysis, you saw, right, indeed. So the non-trivial isotropy always comes with failure of injectivity of your map. And so that means when you're trying to do this hypersurface intersection, to fix your group action, one hypersurface might give you several points. And those are the marked points that then get permuted by the group action. So in the description of the local slice, and so in the Fredholm description, there's sort of an extra group action that kind of permutes those marked points. So there are more marked points in the first place, and then they get permuted. So, and that is harder to describe than one would expect, so I'm not going to go there. That's what I was writing with Tuza a while back. And that needs to get done by hand in every single case anyways. Sort of more useful language to talk a little bit about is the language of groupoids, because that takes care with the topological aspects of these problems with isotropy and sort of trying to define an Euler class. So, and again, it's going to be very, very quick, but so one basic idea here is that you can talk about orbifolds like we did before, or you can talk about them as groupoids. So more precisely, right? So what is a manifold? Right? A manifold is a Hausdorff space that has local charts from our N and smooth transition maps. So an orbifold is simply something where the open sets in Rn can get quotiented out by finite group actions. And then you have local homeomorphisms to your space, like that. So, the example that we had before of what do we have here? Right, Z3 acting on S2. This here is sort of the global chart of my orbifold here. Question?
Is there formula that the number you will get is always the Euler characteristic?
Yes.
Or quotient by the order of
Oh, in this case, yes,
cause
I
of the
guess
bundle
for a
over.
global quotient, I think that's probably true. Yeah, right. Yes, 2/3 here happens to be the Euler characteristic of S2 divided by the order of the group. Indeed, I think that's probably true simply by this construction. Yeah. Right, and I lied. I mean, so. I mean, there's a question whether you want U to be a manifold or U to be an open set in Rn. You know, both actually give the same notion of Hausdorff spaces. Well, you could define an orbifold by allowing finite group actions on manifolds, right? And then taking local homeomorphisms. Because every manifold has all these local charts. And then you just have to sort of make them gamma invariant here. So you can get back to open sets in Rn. This is the simplest example of groupoid language. And the mantra is going to be that once you have an abstract regularization theory that works without isotropy, you just sort of pull that whole theory back and add groupoid, pull it back into a groupoid language, and then you can deal with nontrivial isotropy that way. I'll try and say that a little more precisely. So, all right, there's a lot of words here. So, let's see. What is a groupoid? So, a groupoid is a category with an object space morphisms, and it's a groupoid because all morphisms are invertible. When you have two objects and one morphism, having it be invertible means that there is another morphism, so that the composition is the identity at each of these endpoints, depending on which side you compose that. So, right, and all categories are required to have identity morphisms. So let's see. Étal means in this setting that the space of objects and the space of morphisms are both smooth manifolds. Finite dimensional, usually not compact. And all structure maps are local diffeos. So, what are the structure maps in a category? And so they're maps that tell you what the algebraic structure is. So, let's see. The most important ones are the source and the target map, which know. So if I give you a morphism, the source says what the initial point is, and the target says what the end point is. So those are maps from morphism space to the object space. Then I should know what my identities are. Right? That for every object needs to give me a morphism. And then in a groupoid I also want to know what my inverses are. So for every morphism I should get the inverse morphism.
So you want this to be a local diffeomorphism?
Yes. That's the word état. And finally, I should be able to compose morphisms. And that's where I can use my source and target structure map to make a fiber product that says, oh wait, depending on which order I would like to compose my morphisms in, I have to put the source and target at the different components. This means they're composable, and so I should get a new morphism out. So those are the abundance of structure maps. All right. Proper means that when I take the source and the target map together, that's a map from more to the product of object spaces. And I would like that to be proper in the topological sense, so that means it has preimages of compact sets are compact.
So that's the finite group part.
Sorry?
So am I interpreting correctly that source and target being local diffeos is saying that it's a discrete group, and then proper is saying that it's a finite group?
If your groupoid comes from a global quotient, yes. Yes, I believe that is so. Yeah. Right. So that's all a lot of complicated language. Let me give you the last piece of language, and then we'll actually see how orbifolds have anything to do with groupoids. So the realization now, if I have a category X, that it has a topological realization by, well, if I have a topological category, which this is, because the object space at least has is a topological space. So I'm taking the space of objects and I'm quotienting by an equivalence where two objects are equivalent if and only if there is a morphism between them. That's the somehow obvious idea here. So with that, I can roughly tell you how, when I have sort of an atlas of orbifold charts, how do I get a groupoid? So if I have an orbifold, what should be my object space? Well, I'm just going to take the disjoint union over my atlas of all the domains of my charts. Right? Let's say there's an atlas. And I need these local homeos. And then there are two types of morphisms. One comes from the gamma action on each of the UIs, and the other comes from the transition maps.
Sorry, so for
Question.
Objects and morphism to be smooth manifold, do you mean the space of objects?
Yes. Yes. Right, so here the space of objects is a disjoint union of open sets in Rn. Right. So that's a manifold, right? And okay, since we're here, so let's see, what kind of morphisms do we get? So the morphisms, the component of morphism space that comes from the gamma action is, every element of gamma I can act on every element of my open sets UI. that's the source. So I've sort of labeled my morphisms by the source. And then the target map from here, to objects just takes that element and multiplies. And the transition maps here, oh boy, right? That's. Let me try not try and say what those are, because that's where I would have to tell you how these transition maps really work. But you can imagine. Well, actually, so let's see. I should take the pairs, I guess, U, V, and U times a V, right? Two of these open sets, right? Those are objects. Right, where sort of the psi of U is the corresponding psi of V in the orbifold, right? So that's certainly the points that I need to glue together for the topological realization to become, the space that I think my orbifold is. So I need to think about to what extent that has a smooth structure. Right, and so now if you think about realization, you just think about gluing bits together when there's morphisms between them, and so that means, you essentially, you quotient out by the group action here, and then you glue stuff together exactly with those, with the overlaps.
Sorry, I'm a little confused. So are we going from proper étale groupoid to orbifold right
No,
now?
that was from orbifold to proper étale groupoid.
Okay.
Roughly speaking, because if you wanted to go back, then you'd have to, take your proper étale groupoid and sort of find which morphisms are group actions, which morphisms are transition maps. So I think the equivalence between these two categories is not entirely trivial.
But it is an equivalence.
I believe so. Yes.
Really? So we're not getting a larger class of objects.
Sorry, the equivalence between the category of orbifolds in this sense and the category of orbifolds in this sense.
Okay.
So now you'd have to say what it means for two proper étale groupoids to be equivalent.
But it's fair to say that groupoids are a generalization. That I can find a groupoid that doesn't have such a geometric realization.
Is the realization of a proper étale groupoid always Hausdorff?
Good question. Excellent question.
Yeah, I guess that's related. Yeah.
Related. So, so a quotient topology is Hausdorff if and only if the equivalence relation is proper. Let me write that down. So, lemma, I guess.
Oh, okay.
So, if X is a Hausdorff space, and you have an equivalence relation, then X, what that equivalence is Hausdorff in the quotient topology, if and only if the equivalence relation is proper, in the sense that source and target together are proper. So that has something to do with, if you have a sequence of equivalent things, then in the limit you still want to be equivalent. So right, so that's where the proper comes from. So yes, and so if you construct your groupoid like this, you can check that the realization is in fact the Hausdorff space that you wanted to get. Okay, so that's the big speech, and here is.
Sorry, I'm just
Yes.
confused about one
Yeah,
thing
yeah.
on the last slide. So
Yep.
in the very last statement, this thing you just said, what if we think about x being z,
Yep.
and our equivalence relation is just going to identify everything?
Yep.
Okay. Then x mod equivalence relation is a point, which I think is
Which is
Hausdorff.
pretty Hausdorff, yeah.
But is that equivalence relation proper?
Yes.
It is proper. Really?
Yeah, but, well, it depends on what topology you put on Z, but there's,
Oh.
there are like,
Oh, there's
the
only
compact
finitely many
sets.
arrows between finitely many points. So.
yeah.
Okay,
Oh,
sorry. Yeah,
hold on.
that makes sense.
Right, yes, so if you take now source and target, right, go to object times object, right, so if you take a compact set of pairs of objects,
I mean, this map is
there
it's
are,
an
it's
isomorphic,
exactly,
right? It's a bijection.
right, it's a bijection, so there's exactly finitely many morphisms.
Okay.
Good bullshit detection. So that better be true there. Okay, so here is your favorite example, hopefully, of a orbifold that is not a global quotient. So my topological space is S2, but I'm going to give it somewhat screwed up charts. Right? Namely, I'm going to take a first open set that's a disk. I'm going to quotient it by Z2. That looks like a cone with a bit of a singularity there. But I'm just going to embed that into a little bit more than the upper hemisphere. So that has a Z2 singularity up here. And I'm going to make a Z3 singularity down here by simply taking my second chart to be the disk as well with a Z3 action, and then the quotient is a cone with a somewhat steeper angle, and I can topologically embed that into also a little bit more than the lower hemisphere. And then the two have some nice overlap here. Overlap area going on. So let's see what my proper étale groupoid is with that. Right? So my object space is these two disks. And now my morphism space is, well, somewhat aggravatingly long. So I need to act with Z2 on U1. That already includes the identity elements. Right? So that's good. I also need to act with Z3 on U2. That also has those identity elements. Because these groups are cyclic, I have my inverses there. Because they're closed so far, composition is well defined. And now I want to look at the overlaps. So I'm going to take the annuli in these two. So I would like to take the pairs of points in these two annuli. For which well, if I think of them as sitting in C as the unit disks now, that is that the right thing? I want to say that A1 squared is equal to A2 cube. In terms of arguments, that's certainly the right thing. In terms of norm, I think I could. Well, that now depends on how large I've chosen my annuli here, but I think that's, yeah. Do it like that. Right, and then clearly the source and target map here just takes that point and goes to A1, A2. Whereas here, the source and target map takes a point U gamma and maps it to U and gamma U. So, that, if you glue things together with your realization now, right, so that was X here. Well, topologically, you're going to get, exactly that as 2. Except the smooth structure on object and morphism spaces has now given you a smooth structure on that orbifold S2. Yes.
So for the overlap, are we sort of thinking of it like we use A1 to double cover an annulus and A2 to triple cover an annulus, and then we stick those guys together?
Yes. That's exactly what happens here. Right? Yeah. So here you quotient out that double covers this. And here you 3 to 1, and then within that annulus you should cover. And that right. So here we should let's in fact check that this is a local diffeo. Okay. So let's see if I'm somewhere I don't do I really want to look about A1 times A2. Who do I want to think about? What's the least likely guy that would be a local diffeo here? Well, let me say something that I'm not sure is right. This is not connected with any one specific structure map here, but the point is that if I have any one point here, I can take a little neighborhood that gets so that the 2 to 1 map is a local diffeo, and then it sits in here as a local diffeo. And if I made it small enough, then its pre-image here is also 1 to 1, and so this is nicely a local diffeo. I mean, I can find a lift here. It's just I'm also going to find other lifts. So there's going to be 2 here that go there and 3 here. But when I, for example, look at the source and target map together, these pairs here, are going to be pairs of points here, and so I'll know, like, this pair of points, and sorry, this is quite obviously a local diffeo here, but composition of morphisms and things, just sort of want to get to fundamental domains on which the action is free. Good. So that's an example of a proper étale groupoid. More questions?
So I'm just kind of confused about what happens near the sort of singular points,
right,
where you can't choose a fundamental domain where the axis
yeah,
is free. But somehow that doesn't mess up.
Right.
all these things being local diffeomorphisms.
Well, the source map from here is certainly a local diff. Well, right, the source map is a local diffeo, because it maps u comma gamma to u. Right. And let's see, the target map u comma gamma to gamma u.
Z2 is actually by diffeo.
It's right, and Z2, right, Z2 is discrete, right? So the thing is, going local means I can fix gamma, right? So.
Okay, so obviously it would mess you
right.
up going the other way, but.
Right, but I don't need to go the other way,
Yeah.
right? So, and then identities and composition work exactly the same way. So the crucial thing is the word local, which means that whenever you think about this, you can just, pick one element in your groups. Good. So let's see what happens when we drop the assumption of properness. Right, so what if we just take an étale groupoid? So the easiest example I know of is so my object space is two circles here, disjoint. That means my morphism space better had some identities. So there's the identity source map, I guess, goes from here to there. Oh, so sorry. The identity structure map, right? For every object gives me the identity morphisms. But now I want to do something a little bit funky. I'm going to take an interval, and then I'm going to need the inverses of that interval, and I'm going to need to tell you what its source and target are. So I'm going to take that interval, on both circles, and just make a choice of one being the source and the other being the target. Meaning, so each point here, gets mapped to a source point here and a target point there. So, in the realization, that means that's what we're trying to glue together. Here you can see how these are local diffeos visually. So let's see what our realization is. Well, I'm supposed to take this topological space and identify points between which there is a morphism, which is exactly, I'm supposed to identify that interval with this interval. So I'm going to see that interval just once, but the rest of it, the rest of the two circles will sit there separately. That does not exactly look like a manifold. It is not, let's see, this is not proper because if I take a compact subset in the object space, if I take a product of these intervals here, that's closed intervals, then its pre-image is going to be that interval up here, but that's an open interval because I've asked my morphism space to be manifold, not a manifold with boundary. So that's not compact. Right. And similarly, what happens here is that really this point at the end of the blue interval is 2 points. Yeah, one in each of the gray. Areas, or the gray bits of the circle that don't get identified. Right? And so, as they can't be separated by open sets, right? Because every open set, how does that go now? Right? Open sets in this quotient topology. Well, I ought to take a set down here whose pre-image up here is open. Right? So anything that's open will have to sort of leak into the blue stuff. So they, the neighborhoods here can't, they'll intersect in the blue area, so they don't separate the 2 points. So that's exactly saying that this is not Hausdorff. So that's what we call branching, and I guess it's called manifold because at least of the manifold structure on the object and the morphism spaces. All right, that's not so good news. Good news is that we can use that language, and we're going to get things that. Oh, right, yeah. Important thing to note also is that, well, not only is it not Hausdorff, it is absolutely not clear what its fundamental class should be. Right, you'd think of like a cycle that certainly covers the whole thing, but so the obvious thing would be to take those 2 circles here, cycle, map them in, but then you're double covering the blue stuff, which is somehow not what we think of as a fundamental cycle. We should just get that once. So,
the non-proper tall groupoids can also have much worse realization.
Oh yes.
They don't have they don't have to be as nice as branched manifolds. They could be.
Probably, huh? In one dimensions, I think it's the same. Yeah, but so branched manifold, right? A branched manifold is possibly a special, is a realization of a special étale groupoid. Yeah. Good. So that's the groupoid language. Right? So the philosophy now, if you say you somehow had your moduli space described in terms of a section between nice smooth things, like Banach manifolds or Banach bundles. Okay? And then you have a theory for that, right? So your sort of theory without isotropy, your moduli space is simply the 0 set. Okay? So then once you have isotropy, you might want to add, you want to sort of quotient out by these finite isotropy groups. And the way you do that is you sort of describe everything as étale groupoids and think of the section as a functor in that étale groupoid. And then it has a 0 set that sits in here, and you can take its realizations. And here, nontrivial isotropy is exactly saying that the morphism space, the self-morphism space of points is not just the identity. And if we now have some decent enough regularization theorem when isotropy is trivial, right? So we get some sort of manifolds representing things, and we get integer-valued fundamental class. Then the groupoid language should allow you to get a regularization theorem for finite isotropy, your perturbed zero sets will not be manifolds anymore. They also won't be orbifolds, but they will be branched weighted manifolds. And they will have rational fundamental classes, which I will do in the last 2 minutes. So here's that same branched manifold, except now I'm going to think of this branched manifold here as, well, maybe not the étale category here itself, but the zero set of a multi-valued, well, the zero set of a functor, which means it is, compatible with morphisms, which means it's sort of multi-valued, as we might have to imagine. And that might look exactly like this, groupoid for this branched manifold that we had. But what we are now going to do is we are going to be able to put weights. So from this multisection, we're going to be able to, right, so each of these points here is a zero. And when I have a zero here, I can ask myself, how many branches did or how many values did my section actually have here? And only one of them might have been zero and the other one not. So this might have just been getting weight 1/2. So this is sort of number of values equal to 0 divided by number of values of my section at that point. And so, let's say both of these circles come with weight 1/2. Right? Then in my realization, I can get new weights, by simply adding the weights of the pre-images. The pre-images in the object space. So the beauty is now that I have weight 1/2 on each of these bits of circles, and I have weight 1 on the blue thing, so I can come up with a fundamental cycle here. Oh, right, I'm just calling this S inverse of 0. I can take half time each of these. I can take half of the small circle and half of the large circle. That's covering everything with exactly the right weight. And that is a homology class in this topological space, S inverse of 0, but it's now with rational coefficients. So, a lot of this language was around before. Duza-McDuff sort of imported it into the, connecting orbifolds with weighted branch manifolds and sort of explaining how you can understand the fundamental, or the fundamental classes of orbifolds as weighted branch manifolds, all with an eye towards, dealing with multi-valued perturbations at some point. So, you can now forget about all of this. That is pretty much the reason why I'm not going to talk about isotropy. Because this is a well understood, mostly algebraic framework, and you can sort of put that on top of any other sort of analytic and topological framework that you have. That's not a theorem, but it's a philosophy.